In this lesson, we'll survey the core Python libraries used in data analysis, then use Pandas to import a CSV file, inspect it line by line, correct a misclassified column, and export the cleaned result, so you finish ready to load, inspect, and prepare real CSV data on your own. A Python library is a reusable collection of functions and methods that saves an analyst from writing common functionality from scratch. In data analysis, libraries generally fall into three groups: scientific computing, data visualization, and machine learning or statistical modeling. We'll walk through each group before writing any code. Scientific computing libraries give Python its numerical backbone. Notice the three names on screen: Pandas for tabular data, NumPy for fast array math, and SciPy for advanced scientific functions. We'll look at each one next. Pandas provides data structures and tools for efficient manipulation and analysis. Its core structure is the data frame, a two-dimensional table with labeled rows and columns, and convenient indexing. Notice the row labels on the left, the column labels on top, and the individual cells inside. NumPy's central data structure is the array, which supports fast numerical and array processing along with matrix-style operations. Here we see a simple one-dimensional array and a two-dimensional array, the two shapes you'll encounter most often. SciPy builds on NumPy to provide functions for advanced scientific and mathematical tasks. It covers integration, optimization, signal processing, and statistics. We won't go deep into any one of these. Just know they exist when you need them. Visualization libraries communicate analytical results through graphs, charts, and maps. On screen, you can see the main visualization tools in Python's ecosystem: Matplotlib, Seaborn, Plotly, and the geospatial pair GeoPandas and Folium. Let's look at what each one is best at. Matplotlib is the most widely used Python visualization library, prized for how customizable its graphs and plots are. A simple line chart or bar chart is a typical Matplotlib output. Seaborn is a higher-level library built on top of Matplotlib, and it's especially convenient for statistical graphics. Heat maps, time series plots, and violin plots are all easy to produce with Seaborn. Plotly generates highly interactive web-ready graphs with built-in pan, zoom, hover information, interactive legends, and dashboard-ready charts, useful whenever a viewer needs to explore the data themselves. GeoPandas and Folium specialize in geographic and spatial data. GeoPandas is useful for plotting geographic shapes, spatial coordinates, administrative boundaries, GeoJSON, and shapefile data, while Folium creates interactive layered leaflet maps with markers, boundaries, multiple layers, zoom controls, and pop-ups. Machine learning algorithms use datasets to develop models and generate predictions. Scikit-learn and stats models are the two main libraries in this category, and this image shows how they fit into the broader algorithm ecosystem. Scikit-learn includes tools for regression, classification, clustering, and model evaluation, and it works closely with NumPy, SciPy, and Matplotlib under the hood. StatsModel supports data exploration, statistical model estimation, and statistical tests, rounding out the modeling side of Python's ecosystem. These libraries rarely work alone. Pandas structures your data, NumPy and SciPy handle the math, Matplotlib and Seaborn visualize it, and Scikit-learn or StatsModels model it. Keep that relationship in mind as we move into actually loading data with Pandas. Data acquisition means loading and reading data from a source into Python. Before you can do that, you need two things: the format, meaning how the data is encoded, often shown by the file extension, and the file path, meaning where the data is stored, whether that's a local folder or an online location. Here's the raw CSV we'll work with. Each physical line is one row, commas separate the values into columns, and the very first line holds the column names. Look closely at the last row. The price value after Volvo, diesel, 106 is missing, which we'll need to handle later. The first line of every Pandas script is this import. We're importing the Pandas library and giving it the short conventional alias PD, so every later call can be written as pd.something instead of the full library name. Next, we store the CSV's location in a variable called file.path. This is exactly the file path concept we just discussed. It must point to the correct file, whether that's a local folder or a full URL. Now we call pd.readcsv, passing in file path, and store the result in a variable named df. Readcsv is the pandas method that reads comma-separated data. File path tells it where to find that data, and df is the data frame that receives the result. This is what df looks like right after loading. A table with make, fuel type, horsepower, and price as columns, and one row per automobile from the CSV. Read.csv normally assumes the first row holds column names. For a file that has no header row, you add header none, and pandas will assign temporary integer labels instead of treating that first data row as headers. With header none, the columns are no longer named make, fuel type, horsepower, and price. They're just 0, 1, 2, and 3, which is exactly why we usually assign meaningful names right after. df.head prints the first 5 rows of the data frame by default, giving you a quick look at what the data actually contains before doing any analysis. df.tail is the mirror image of head. It prints the last 5 rows by default. Together, head and tail give you a quick sense of the beginning and end of your dataset without printing everything. Integer labels like 0, 1, 2, and 3 are hard to interpret. Here we store readable names in a headers list, then assign df.columns equal to headers, which replaces the existing column labels with make, fuel type, horsepower, and price. Calling df.head again now shows the same rows, but with make, fuel type, horsepower, and price as readable column headers instead of plain numbers. df.dtypes reports the data type assigned to every column, while df.info summarizes the index columns, non-null counts, data types, and memory usage all at once. Correct data types matter because they determine which calculations and operations you can safely apply. df.describe summarizes the numerical columns with statistics like count, mean, standard deviation, minimum, quartiles, and maximum. Adding include equals all also summarizes the non-numeric columns, and you may see nan wherever a particular statistic doesn't apply to that column's type. This compact table is what numeric summary looks like: count, mean, standard deviation, minimum, the quartile breakpoints, and maximum for each numeric column. The price column may be stored as text because of that missing value. pd.toNumeric converts values to numeric form, and errors equals coerce means any value that can't be converted becomes a missing value instead of stopping the program. ISNA identifies which entries are missing, returning true or false for every row, and sum adds those up to give a single count of missing prices in the column. Printing missing prices confirms exactly one price value is missing in our sample data, the Volvo row we spotted earlier when we first looked at the raw CSV. To CSV saves the data frame as a new CSV file at the path you specify. Here it writes our cleaned data to automobile.clean.csv, completing the round trip from raw file into pandas and back out to disk. Here is the entire program we built line by line. Import pandas, define the file path, read the CSV, inspect it with head, tail, dtypes, and info, generate descriptive statistics, fix the price column and count missing values, then export the cleaned data frame. Every step you just watched is a single line in this script. Let's recap the full workflow. Identify the data format, locate the file path, import pandas, read the CSV into a data frame, inspect sample rows, assign meaningful headers when necessary, verify data types and structure, calculate descriptive statistics, correct data type problems, and inspect missing values, and finally export the cleaned data frame. You are now ready to load, inspect, and prepare CSV data for analysis in Python. Run it, inspect it, understand it. Build the next step with confidence.